All right, so we are going to be working on Chapter 5, Lesson 4. So what we're going to be learning is we're going to be working on factoring polynomials. So some of the goals we're going to learn is factoring polynomials and then simplifying polynomials with quotients by factoring. So how does factoring apply to geometry? So suppose the expression 4x squared plus 10x minus 6 represents the area of a rectangle. Factoring can be used to find the possible dimensions of a rectangle. So if this was my area, the factors would be the two things that I would multiply to get that area. So this length times this width would give me that area there. So factoring helps us figure out what those two factors are. So factoring polynomials. Whole numbers are factored using prime numbers. For example, 100 is equal to 2 times 5 times 5. So these are all prime numbers that are factors of 100. So if I multiply these all together, it equals 100, right? Many polynomials can also be factored. Their factors, however, are other polynomials. Polynomials that cannot be factored are called prime. So the table below is going to summarize the most common factoring techniques used by polynomials. So a lot of these we actually learned in Algebra 1. So let's just go over a few of these factoring techniques. And you probably want to write these down in your notes and have them readily available for you to do when you're working on your problems. So if you have any number of terms, you always want to start with the factoring technique of finding the greatest common factor. So if you have a polynomial like this one, if you notice, they all have a and b in common. They all have a factor of a and b in common. So if I were to divide a, b from each one of these, in the parentheses, you will find what's left over. I would have a squared b plus 2a minus 4b. And you can always check to see if it makes sense, because if I were to use a distributive property and multiply this back out, it would just give me this. The next one is if you have two terms, right? If you have a polynomial with two terms, a lot of times you'll find that that is the difference of two squares, the sum of two cubes, and the difference of two cubes. The sum and difference of cubes is probably a new one, but we've definitely done differences of squares before in Algebra 1. So for example, a difference means subtraction, and squares means your two terms are perfect squares. So if I have a squared minus b squared, that's going to be equal to a plus b quantity times a minus b quantity, right? So I have a plus b, a minus b. That would, if I multiply those together, those give me a squared minus b squared. Again, because if I were to do a times a gives me a squared, a times negative b gives me negative ab, b times a gives me ab, b times b gives me negative b squared, and obviously the middle terms would cancel out, leaves me with that. Sum and differences of cubes, pretty similar. If you have perfect cubes being added together, it gives you this. If you have two cubes subtracted, it gives you this. So again, these are probably easier to reference, so I would definitely write these down. And then if you have three terms, that's what's known, can be a perfect square trinomial. So if you have perfect squares on the outside plus those two same terms on the inside, that's usually going to be that same quantity squared. So you'd have a plus b squared. And same thing, if you had the subtraction in the middle, it would be the same idea, except you have a minus b squared. And if you have any general trinomials, this is what is known by factoring by grouping, and we'll get into a problem like that. Or if you have four or more, similar thing, you'll have to group them together and factor each one independently. So let's look at some examples where we encounter this. Whenever you factor a polynomial, always look for a common factor first. Then determine whether the resulting polynomial factor can be factored again using one or more of the methods listed in the table above, which we just saw in the last slide. So let's look at this one. So we were given this example, right? Factor 6x squared y squared minus 2xy squared plus 6x cubed y. We would want to look for a common factor first. Now, if I look at all three of these terms, I can see that 6, negative 2, and 6 all have 2 in common as a factor. And if I look at the variables, well, they all have x in common. So that's x squared, x, and x cubed. So they all have an x in common. And then here I have y squared, and y. So they have a y in common. So the greatest common factor out of both of these, I can see if I break them apart, right? I can see that they all have a 2 in common as a factor. They all have an x in common, and they all have a y in common. So I would factor out 2xy from each one, right? That's the greatest common factor. And so if I factor that out, I divide it out, it'll leave me with the 3xy minus y plus 3x squared. So you can, again, always check this result by using the distributive property, and if you multiply this out, it would get you right back to the original problem. So it's an easy way to check yourself to see if you're doing it correctly. The greatest common factor is also used in grouping to factor polynomials of 4 or more terms. So here's an example. If I have a cubed minus 4a squared plus 3a minus 12, now notice that there's no common factor between all 4 terms, but if I factor it by grouping, which means I'm going to group the first 2 terms together and then group the second 2 terms together, that will kind of make the problem kind of divided up into 2 separate problems. So if I group the first 2 terms together, what is the greatest common factor of these 2 terms? Well, I have a to the third, and then I have minus 4a squared. Well, they both have a in common, but not only do they have a in common, they have a squared in common. So I would factor out a squared from both of these. And if I look at this parentheses here, what do these 2 terms have in common? Their greatest common factor would be 3. So again, I factored out a squared from this parentheses, and it leaves me with a minus 4. I factored out or divided out 3 from this parentheses, leaves me with a minus 4. So now I factored each one of these separately. Now I'm back to having 2 terms. I have this term plus this term. Now, if you notice, both of these terms have something in common. If you notice, they have that parentheses in common. That factor is in common. So I can divide that out. I can factor that out. So if I factored out a minus 4, it leaves me with a squared plus 3. So let's go ahead and look at one more. So that would be the final simplified answer. Neither one of these can be simplified any further. So that's as simplified as it gets. Let's look at an example. This example is going to have, we can have 2 or 3 terms, so we're going to go over a couple of them. So if you were given this one, you have 5x squared minus 13x plus 6, and you are asked to factor this, right? Again, the first thing you want to do is you want to look to see if you have a common factor between all 3 of these terms. The answer is no, we don't have anything that we can divide or factor out of either of all 3 of those terms at the same time. So what we're going to do is we're going to find the coefficients of the x terms, and we're going to split this up into 2 terms, okay? And the way that we know how to split this up is these 2 terms have to add up to negative 13, but have to have the same, have to multiply to the same thing as the outside numbers. So if you notice the outside numbers, 5 and 6, well, 5 times 6 is 30. So I have to pick 2 numbers that multiply to 30, but add up to negative 13. And those 2 numbers would be negative 10 and negative 3. Easy way to do this, if you couldn't think of that off the top of your head, list all the factors that multiply to 30, right? Like 1 times 30, 2 times 15, 3 times 10, 5 times 6, and then figure out which pair of factors would add up to 13. So we're going to rewrite this expression using negative 10 and negative 3. Okay, so again, I'm going to take this middle term and I'm going to split it up into negative 10 and negative 3x, right? So now this is equivalent to this one, but now if you notice, since I'm split up those middle terms, now I have 4 terms, and you might ask, why is that important? Well, because now I can use grouping again. I can group the first 2, and then I can group the second 2 and use factoring by grouping like I did in the last one. So again, I group the first 2, group the second 2. Notice how that's minus 3x, so I keep that negative sign with the 3x there, and I can just put a plus sign there because these mean the same thing, right? Using the associative property. And so now I have to look, what is the common factor of the 2 terms in this first parentheses? Well, they both can factor out a 5, right? And they both can factor out an x. So I would factor out 5x from both of those. And then if I look here, what can I factor out of these? I can definitely factor out a 3. Now, I'm going to go ahead and factor out negative 3, and I'm going to explain why. If I factored out 5x from here, it leaves me with x minus 2, right? X, and then I have minus 2 there. Again, you can check it by multiplying to make sure it gets me back here. And then here, the reason why I want to factor out negative 3 is because notice if I divide out negative 3, that leaves me with positive x, and then negative 3, or positive 6 divided by negative 3 gives me negative 2. And if you notice, these two parentheses are exactly the same. So this term and this term now have a common factor of x minus 2. I want them to be there. If I were to only factor out a 3, then it would have left me with negative x plus 2, which would not match. I want them to match. I want these two parentheses here to match because they want them to be the common factor. So if I factor out x minus 2, it leaves me with 5x minus 3 in the other parentheses. So now I was able to factor it completely apart. This is as simplified as it gets, and this would be the answer for A. Let's look at another one. So I have 3xy squared minus 48x. So again, I'm going to look, okay, well, if I have two terms, do I have any greatest common factor of both of these? And the answer is yes. Both of these are divisible by 3, and both of them are also divisible by x. So my greatest common factor is going to be 3x. So I'm going to go ahead and factor out the 3x, which leaves me with y squared minus 16 in the parentheses. Now, remember the difference of squares. If I have two perfect squares subtracting from each other, those do factor out as a difference of two squares. Notice y squared and 16. Y squared and 16 are both perfect squares because that's just y times y, and that's 4 times 4. So it would fall into a difference of two squares there. So this would actually factor out into y plus 4 and y minus 4, because if I multiply these two parentheses together, it gives me y squared minus 16. So now I've completely factored this apart, and that's as simplified as it gets. Let's look at another one. Here I have c cubed d cubed plus 27. Now if you notice here, these aren't perfect squares, but they are cubes. And you can see c cubed d cubed is just cd cubed, right? cd times cd times cd is cd cubed. And 27 is actually 3 cubed. 3 times 3 times 3 is 27. Thus, this is actually a sum of two cubes. And again, that chart that I showed you early on, which I asked you to write down, this is what it said. It said if you have a cube plus another cube, that's equal to this algorithm here. It's equal to a plus b parentheses times parentheses a squared minus ab plus b squared, right? So basically we get to fill this out here. So again, this is my original problem. If I rewrite it as cd cubed plus 3 cubed, because that's what this equals, now I can see, I can kind of plug it in into this algorithm here. So it's going to be c plus 3 parentheses, and then parentheses cd squared, right, because it's a squared, minus, right, minus ab, so minus 3 cd, right, the a and the b, right, plus b squared plus whatever my second term was, which was 3 squared. And then now I can go ahead and just finish simplifying. Obviously, there's nothing to simplify in the first one, but if I do cd cubed minus, and then 3 times cd is 3cd, and then 3 squared should give me with 3d plus 3, cd plus 3 times c squared d squared minus 3cd plus 9. So this is the simplified answer here. So again, this is using this factoring technique of the sum of cubes. Let's look at the last one here. So here I have m to the 6 minus n to the 6. Now you might ask yourself, we didn't learn about 6th power ones, but there's something that you should remember as far as your rules of exponents, right? This polynomial could be considered the difference of two squares or the difference of two cubes. The difference of two squared should always be done before the difference of two cubes, because this will make the next step of factoring much easier. So again, if I think about this, m to the 6 minus n to the 6, these are actually perfect squares. This is actually m to the 3rd squared, right? Because that's going to give me m to the 6 minus n to the 3rd squared. So if I think about this, this is just this perfect square minus this perfect square. So that means I can use, again, the difference of two squares. So if I factor this as a difference of two squares, that would give me m to the 3rd plus n to the 3rd times m to the 3rd minus m to the 3rd, right? Just plugging in that a and b, which happens to be m to the 3rd and n to the 3rd. Now, if I look at it, probably looks a little simpler now. What do you notice here? This is a sum of two cubes, and this is a difference of two cubes, right? So sum of two cubes, difference of two cubes. So I get to use these things kind of in parallel here. So m to the 3rd plus n to the 3rd is going to fall into this category. So literally I can kind of follow this pattern here, and instead of using a and b, I'll use m and n. And then the same thing here. m to the third minus n to the third. Instead of a and b, I'll use this one. And so when I factor it out, here's the sum of the cubes. Here's the difference of the cubes. Again, just following these kind of simple patterns and algorithms. And then that would be the simplified answer. These can't be factored any further. So let's finally here, we're going to be talking about simplifying quotients, right? So in lesson 5.3, you learned to simplify the quotient of two polynomials by using long division or synthetic division. Some quotients can be simplified using factoring. So quotients of two trinomials. So if I were given this problem, x squared plus 2x minus 3 over x squared plus 7x plus 12. Well, I'm going to go ahead and start by examining the problem and notice that I can actually factor this trinomial on top, and I can also factor this trinomial on the bottom. If I factor these, right, this trinomial actually just factors out to x plus 3 times x minus 1. So, because I know x times x is x squared, x times negative 1 is negative x, 3 times x is 3x, which if I have negative 1x plus 3x, that makes positive 2x. And then positive 3 times negative 1 is negative 3, right? Same thing here. I factored out x squared plus 7x plus 12 factors out into x plus 4 times x plus 3. So if these get factored out, now I know that this times this over this times this, right? What do you notice about these two factors on top and bottom? They're exactly the same. I can see the factor x plus 3 in the numerator, and I can see x plus 3 in the denominator, and they would cancel each other out, right? Or give you 1 over 1, right? So the factor in the numerator and the denominator would cancel each other out. And so it would just leave me with x minus 1 over x plus 4. Now the thing that we have to assume is that x can never be negative 4 or negative 3. Why is that? Because if x was negative 4, I would get a 0 in the denominator and it would give me an undefined number. Or in this other one, if x was negative 3, it would also give me 0 here, which again gives me a 0 in the denominator, which would give me an undefined number. So we can never have zeros in the bottom or else it gives us an undefined number. So that's why we're going to assume that x cannot be negative 3 or negative 4, because we can't have zeros in the denominator. So this would be our simplified answer, right? This simplifies to this, and if x isn't negative 3 or negative 4. So that's kind of how you would work with quotients, right? You go polynomial on top and bottom, factor them out, cancel the terms that are the same, and then again, just make sure you identify which x values cannot be true there because you would get undefined numbers, and that is your simplified answer. Thank you guys for watching, and I'll see you guys next time.